Why, hello. Today we're going to go on to section 17.5, which deals with the curl and the divergence. So without further ado, let's define the curl. The curl is something that is applied to a vector valued function. The curl does not make sense if you're applying it to some scalar function. So you have to have an I, j, and a k component. Okay? Now, you could have the I and the j be zeros, but I mean, you have to have components. Now, the way you compute the curl, the easiest way to remember it is the curl of a vector valued function gives you or renders you a vector valued function. And the way I remember it is this. We can write it as curl of f. It's easier to type it that way. In most engineering textbooks, they type it as del cross f. Now remember, when you take the cross product, think of, what I want you to think of is, think of this del here. And she made it bold so she didn't put an arrow over it, but it's really a vector. Think of this as sort of a vector operator. The vector operator being the partial with respect to x times I, plus the partial with respect to y times j, plus the partial with respect to z times k. That del being that. So, if I apply del cross f, just like we did cross products back in our first chapter, chapter 13, we put I, j, and k across the top, and then across the second row we write partial with respect to x, partial with respect to y, partial with respect to z, and then we put our components p, q, and r across the bottom. And we do cross product just like we always did, except like when you eliminate the row and the column that I is in, and you go I times. When you go this times this, it's not really times, it's this operating on this. So you get the partial of r with respect to y minus the partial of q with respect to z. Then you eliminate the row and the column that j is in, and remember it's minus j. Always start in the top left-hand corner. So partial with respect to r of x, this partial with respect to x of r minus the partial with respect to z of p, and then plus k, eliminate the row and column that k is in, and you'll have the partial with respect to x of q. She has a little typo here. I didn't notice that when I was proofreading. So those of you at home, when you print it out, it will be fixed. But for right now, this should be partial with respect to q of x minus partial with respect to p of y. Now the good news is nobody's going to memorize this. I have students that try to dutifully copy this down in their notes. You're not going to do that. You're going to write it as a determinant and use that every single time that you do it. Okay, coming right here, let's do one to practice. They want us to find the curl of f, where f is the valued vector function whose components are this, this, and this. So del cross f is equal to, we go I, j, k across the top. Second row is partial with respect to x, partial with respect to y, partial with respect to z. This x component is x squared yz. The y component is xy squared z. And then we have xyz squared. Okay? And when we do that, what do we get? This is equal to I times, now, I eliminate the row and the column that I is in. So I go the partial, what's the partial with respect to y of this? Well, the partial of this is going to be xz squared. Minus, and then we take the partial with respect to z of this, which is xy squared. Minus j times, we eliminate the row and the column that j is in. Partial with respect to x of this is yz squared. Minus the partial of this with respect to z is x squared y, plus k times, eliminate the row and the column that k is in, partial with respect to this is y squared z, minus partial of this with respect to y is x squared z. And to get the answer that they have in the back of the book, or in the answer key, you'll have I times, notice you can factor out an x here, and that gives you z squared minus y squared, plus j. Now we could factor out a y here, and notice this is minus y times z squared, so it's minus z squared, and minus a minus makes it a plus x squared, plus k times, we could factor out a z here if we wanted to, and that would give us y squared minus x squared. Okay, and notice, when you take the curl of a vector valued function, you get a vector valued function. The curl of a vector gives you a vector. The curl of a vector valued function gives you a new vector valued function. And right now you ask why, but in this section we'll get a little of an inkling why you want to know what the curl is. And not until the end of the chapter will we truly see what you use it for. So this section is pretty much how do you do it and get the answer. All right, now what I chose to do is I printed out a vector valued function. Okay, this is the direction field of a vector valued function, and I did it on Maple. And I just defined, I wanted to get one that looks like, think of this as a fluid flow. All right, this is a cross section of a fluid flow. And so at each of these little points, the little arrows showing me in what direction the fluid is flowing, and its length is giving you the velocity. So the longer the arrow, the faster the speed. So if you look, this fluid flow looks like, you know, like it does when it goes down your bathtub drain. You know, it's going around in a circle like this as it's going down. And the function, I wanted to pick one that would make it flow around. And so I played with it for a while, and I came up with this one. Minus y times I plus k times j. And notice it does have a k component. It's just 0 times k. Okay? Let's figure out what the curl of this easy function is. Okay, so if I want to get the curl of f, which we're going to usually write it as del cross f, that's going to be, you're going to go I, j, k, partial with respect to x, partial with respect to y, partial with respect to z. And then we put down our x component is minus y, our y component is x, and then 0. And computing this is quite easy. This gives me I times, eliminate the row in the column that I is in, so I have 0 minus partial with respect to z of x is 0. Notice I picked a really nice function. Minus j, pardon? Partial with respect, notice you're going this minus this. In fact, let me write it out. It's the partial with respect to y of 0. Well, the partial of 0 is 0. Minus, we have the partial of x with respect to z. Well, since x doesn't have a z in it, it's considered a constant, and the partial of a constant is 0. So we have 0 times I. Minus j. Now for j, we're going to go this, the partial of 0 is always 0. Minus a minus is a plus, and this is the partial of y with respect to z, which gives me what? 0. That's another 0. Then we're going to go plus k times, eliminate the row in the column that k is in, the partial with respect to x of x, minus a minus is a plus, the partial of y with respect to y. Well, the partial of x with respect to x is 1. Partial of y with respect to y is 1. So this is really just 1 plus 1, which is 2. Okay, so we figured out the curl of this function that I just did is just the vector 2k. Now, I'm not proving this right now. I'm not proving it at all. I can't. I need some high-powered theorems at the end of the chapter to prove it. But what I want you to show, because people go, why do they call it the curl? Why does anybody care? Where does it come from? Just to give you an idea, here's a vector-valued function in which it's representing something swirling around the origin. Notice, if I wanted to draw the vector 2k, how would I draw it? It has an x component of 0, a y component of 0, and a z component of 2. It's coming out of the paper like this, right? Well, the way I think of the curl is this. The curl represents, think of it as like you have a little kid's toy. And you've got, this is the curl, del cross f. Okay, it's a vector, all right? Now attached to the base of this vector, think of it as a little paddle wheel. And it's got little paddles on it. All right, now what it's saying is if you take that little handle and place it where this vector is, all right, the little paddle is going to swirl. You follow? I put this here, and here's my little paddle wheel with my little things going here. You with me? And since it's swirling, what's it going to make this do? My little paddle wheel. My paddle wheel is going to swirl in the direction that the fluid is rotating. So when you think of this as fluid flow, when the curl does not equal 0, and in this particular case, it doesn't matter, you know, it's 2k no matter what point you pick. It's saying if you take your paddle and place it at that point, so here's the curl, 2k. But at the base of it is this little paddle wheel. If you place it that way, you're going to have swirling around the base of it. And so it's showing you in what direction to place your paddle wheel so you will get maximum curling. And that's why it's called the curl. Now, what do you think happens when the curl is 0? And again, we're not proving this right now. I'm just giving you a sense of why anybody cares about this. If the curl is 0, you're not curling. So what does that mean? You're getting straight fluid flow. You're not curling. You with me? So here we're getting little jetties going around. All right, now what else do we care about the curl? All right, now a couple of these theorems at this point, you go like, this is pretty dry stuff, but let's just go over it anyway. If f is a function of 3 variables that has continuous second-order partial derivatives, we have this lovely theorem that says that if you take the curl of the gradient of f, you will always get the zero vector. Okay, now let's prove it. Let's prove it for just a second and see where it comes from. Notice, let's review before we even prove it. Notice if f is a scalar function, that means you end up with like z equals f of x, y, z. All right, a few chapters ago we learned how to do the gradient of f. When we did the gradient of f, what did we get? Partial of f with respect to xi plus partial of f with respect to yj plus partial of f with respect to zk. When we had a scalar function, when we took the gradient, what did we get? We got a vector valued function. But notice the gradient acted on a scalar function, like f of x, y, z equals x squared plus y squared plus z squared. Today, we have a function f which is vector valued. So it's going to have an x component, a y component, and a z component. When we take del cross f, which we can also write as the curl of f, what do we get? We get a vector valued function. Or you can call it a vector field. Okay? So the curl acts on a vector valued function. The gradient acts on a scalar function. Both of them produce vector valued functions. All right, now what we want to prove here is if you have, notice, if f is a scalar function, when I take the gradient of f, what do I get? A vector valued function, don't I? And so we're claiming if I take any scalar function, take the gradient of it, that produces a vector valued function, I'm claiming the curl of that will always turn out to be 0. In other words, you won't have any curling. All right, how do I do it? Okay, well, if f is some scalar function, the gradient of f, again, is the partial of f with respect to x times I, plus the partial of f with respect to y times j, plus the partial of f with respect to z times k. Now, if we want to get the curl of the gradient of f, we go I, j, k, partial with respect to x, partial with respect to y, partial with respect to z. And here we have partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. Right? That's how you take the curl of something. But you feel it. See, gradient of f has this for its x, y, and z components, so that's what goes here. All right, so this is equal to I times, eliminate the row and the column that I is in, and I have the second derivative because I'm taking the partial of f with respect to z and then taking the partial of that with respect to y. So I have the second derivative of, I'm going with respect to y and with respect to z. When I go this way, it's the second derivative, and we're going with respect to z with respect to y. Minus j times, this is the partial with respect to x of this, so it's the second derivative, and we're going with respect to x and with respect to z, minus, when you go this, it's the second derivative with respect to z, but first you took with respect to x, plus k times, eliminate row and column that k is in. When I take the partial of this with respect to x, but you're taking the partial of f with respect to y, so it's a second derivative. First with respect to y, then with respect to x, minus, here, take the partial with respect to y, but first you took the partial with respect to x. Well, come back here. Look at this. What do we know about these two partials? They're equal. Clairaut's theorem, remember? These are equal. Those are equal. So we get 0 times I plus 0 times j plus 0 times k. So what we have just proven is a nice little theorem that will come in handy later on. The curl of the gradient of any scalar function always turns out to be 0. Okay. Now here's a nice little sidekick. Suppose f is a conservative field. Then the curl of f will always turn out to be 0. What did it mean to be conservative? You were conservative. F is conservative. If I tell you f is conservative, then that means you can find little f so that the gradient of little f is big F, right? So the curl of f, big F, is the curl of the gradient of little f, because we can substitute this for this, and we just proved the curl of the gradient of any scalar function is always 0. Now you guys are looking at me like, why is she doing this, Mrs. Strocko? Because there's this wonderful little theorem, which I'm not going to prove, is that this is true both ways. And this is very, very helpful. If f is a vector field whose components have continuous partial derivatives, now that's big. You take your partials, and each of those partials is continuous. I did it the one way. If I'm conservative, the curl is equal to 0. I'm not going to do it the other way for right now. We'll be proving it in a few sections from now, but I'm giving it to you now. The following are synonymous. Knowing f is conservative is synonymous with del cross f equal to, she should have had an arrow across here, equal to the 0 vector. Remember, to be conservative means that you have a potential. You can find some scalar function f so that the gradient of little f is equal to big F. That's what conservative meant. Why did I care about that? I cared about that because, remember, if I was taking the integral along some curve of f dot dr, all right, some curve from here maybe to here, and doing that for the curve was a lot of work. But we proved that if f was conservative and you could find this little potential f whose gradient was equal to big F, what we proved is this is equal to little f evaluated at the final point minus little f evaluated at the initial point. And that was big news to be able to do that. It was a lot easier to do that, to evaluate the integral doing that. All right? So now, if I have a vector function and I'm thinking, oh, I wonder if it's worth my while trying to see if it has a potential, if there's this scalar function, we now know that if the gradient is 0, then it's worth my while. If the gradient's not equal to 0, then it doesn't have a potential. So there won't be a little scalar function f for which I can take its gradient and have that equal to the original function f. So note, just from the thing that we were looking at with my little thing coming around, if the curl of f is 0 at a point P, then the field is free of rotations at P, and f is called irrotational. It means I'm not curling. All right, so what we have done so far is we've learned how to do how to do the curl, and we have found that the following 3 things are synonymous. If the curl of f is 0, that means the same thing as f is conservative, which means the same thing as you can find little f so that the gradient of little f is equal to big F. And finally, if you wanted to do f dot dr, you can do it by taking f at your final minus f at your initial. Okay? All right. Now, we really haven't proven, we proved this going one way. If f is conservative, we proved this is true. We haven't gone the other way, but that will come. Okay, now let's look at a problem here. Determine whether or not the vector field is conservative. If it is conservative, find the function for which f is equal to the gradient of little f. Now, I could have made it a lot easier. Instead of saying find the scalar function f such that the gradient of little f is equal to big F, I could have just said determine the potential of big F, because that function whose gradient is equal to big F is called the potential. Okay, so I say, is f conservative? Is big F conservative? Well, remember, del cross f equals 0 means the same thing as f is conservative. So if I take the curl and I get 0, f's conservative, let's find let's find our potential. If del cross F is not 0, and notice this is the 0 vector, I should put an arrow above it, then F's not conservative, it's not going to have a potential. It's not worth my while. So this particular function, if I want to get del cross F, what am I going to do? I'm going to go I, J, K. Across the middle row, it's partial with respect to X, partial with respect to Y, partial with respect to Z. And you need to practice. A lot of times students think, they'll do a couple curls and they're done. No, no, no. You want to practice. So I get 3Z squared for my X component, cosine Y, 2XZ. All right, and when I go to do my partial here, let's see what we have here. This is equal to, eliminate the row and the column that are I's in, and notice we're taking partial with respect to Y of 2XZ minus partial with respect to Z of cosine Y. Okay? All right, what do we get for the first one? What's the partial with respect to Y of 2XZ? What's this? 0. And what's the partial with respect to Z of cosine Y? 0. Okay, then we're going to go minus J times, eliminate the row and column J is in, so I have partial with respect to X of 2XZ minus partial with respect to Z of 3Z squared, right? So far I have this equals 0 times I. So the partial with respect to X of 2XZ is 2Z. And the partial with respect to Z of 3Z squared is 6Z. Plus K, so we have here 0I, this is minus 4Z with a minus plus 4ZJ. Now we have to go plus K times, eliminate the row and column K is in, partial with respect to X of cosine Y minus partial with respect to Y of 3Z squared. Well, what's the partial with respect to X of cosine Y? What's this? 0, because Y is considered a constant. And partial of 3Z squared with respect to Y is 0. So I have del cross F is equal to 4ZJ. Does that equal the 0 vector? The 0 vector has X, Y, and Z all equal to 0. I've got a Y component that's not equal to 0. That does not equal 0. So since del cross F is not equal to 0, the curl of F does not equal the 0. Notice this is a vector. It doesn't equal the vector that's 0, 0, 0. That tells me F is not conservative. So guess what? F does not have a potential. You can try all you want to get that little scalar function F whose gradient is equal to big F. It's not going to work. It's like putting a square peg in a round hole. It's not going to work. It's not worth our while. So for this problem, what did I do with it? Right here, they say, determine whether or not my vector field is conservative. I say, no, it's not conservative. I cannot find the potential. It does not exist. Okay, this one. They want me to find whether or not this is conservative. If it is conservative, let's find out what its potential is. Okay, well, first of all, let's figure out del cross F. So across the top, I go I, J, K, partial with respect to X, partial with respect to Y, partial with respect to Z, e to the Z, 1, and X e to the Z. And this is equal to I times. I eliminate the row and column that I is in. Now, what's the partial with respect to Y of X e to the Z? 0. Minus, what's the partial with respect to Z of 1? 0. Minus J times, eliminate the row and column that J is in. What's the partial with respect to X of X e to the Z? E to the Z. Minus the partial with respect to Z of e to the Z is e to the Z. Plus K times, eliminate the row and column that K is in, partial with respect to X of 1 is 0, minus partial with respect to Y of e to the Z is 0. So I have 0I plus 0J plus 0K, which equals the 0 vector. So what does that tell me? Since del cross F is the 0 vector, that tells me F is conservative, which means it has a potential. There is some scalar function F. Do I know what it is at this point? No. But if I take the gradient of F, which is the partial of F with respect to x times I, plus the partial of F with respect to y times j, plus the partial of F with respect to z times k, this will equal big F. So this x component must equal this x component. This y component must equal this y component. And this z component must equal this z component. So now we're going to try to build the potential. So I have the partial of F with respect to x must equal e to the z. So what am I going to integrate with respect to? With respect to x. So my first guess is F should be, now what's the integral of e to the z with respect to x? X e to the z, right? Because e to the z is considered a constant. Plus, now notice you would check this answer by if you differentiate this with respect to x, you should get this. Well, if you had something in terms of y's and z's, so you had like a y squared or a y squared plus z cubed or a y squared z to the fifth. If it's just in terms of y's and z's, when you take the partial of this with respect to x, it disappears, doesn't it? And you would just have this. So this is my first guess. Okay? Now, now we're going to tweak this as we go. We're going to say, do we have to add any pieces that have phi of yz? All right, well now we have the partial of f with respect to y is equal to what? 1. If I integrate both sides with respect to y, I'm going to get f equals y plus something with maybe x's and z's in it. Now, you're not going to add something with x and z's in it. You're just going to look at your first guess, and you say, oh, there's the something with x's and z's. I already got it. There's my something with x's and z's here. So it's okay. I can have something just in terms of x's and z's. And notice this phi of yz is going to be y. Plus, we might now just have something with just z in it, right? Because now we check ourselves. If you take the partial of this with respect to x, you're going to get e to the z, because the partial of this with respect to x is nothing. And if this is totally in terms of z, it's going to be nothing. And if I take the partial of this with respect to y, this is 0, that's 1, and that would be 0. So it works. Now let's check the z part. We have the partial of f with respect to z is x e to the z. So if I integrate that with respect to z, that would give you f is x e to the z. And I go, well, I already have that. So I don't need another piece with z's, just z's in it. This is my potential. So the potential of my function f of x, y, z is x e to the z plus y. And if you want to check yourself, the gradient of this function is equal to your vector valued function big F. Okay, now we're going to play a little bit. I'm actually doing numbers 9, 10, and 11 right out of the textbook. All right? It's not printed out in your sheets. What I did is I just Xeroxed them is what I did. All right? But let's look at what first we're just going to do part A, and then we're going to come back and do part B after we learn what the divergence is. Now let's read the directions here. The vector field F is shown in the xy plane and looks the same in all horizontal planes. Determine whether the curl of F is the 0 vector. If not, in which direction does the curl of F point? Remember, the curl of F is a vector. Okay? All right, now, let's just write out what the curl is. All right? Notice, if you have a function f, it's equal to something p times I plus q times j plus r times k. All right, just remembering what the curl of f is. We did I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, and then we put p, q, and r here. And therefore, the curl of f is equal to I times, now you eliminate row and column that the i's in, so we have the partial of r with respect to y minus the partial of q with respect to z. Now normally we go minus j, but why don't I go plus j and just change the order of the subtraction if that's okay with you. So if I eliminate the, normally we go minus j and then this minus that. Why don't we just go this minus this? So it's the partial of p with respect to z minus the partial of r with respect to x. Everybody with me? I eliminated the row and column that j is in. And normally we had a minus here, and then you'd go this minus this, but I'm just going to change the order of the subtraction. And you go the partial of z with respect to p minus the partial of r with respect to x. And then we have our k piece. Eliminate row and column that k is in, so we'll have the partial of q with respect to x minus the partial of p with respect to y. Now you look at this and you go, oh my goodness. They want me to look and say, looking at that fluid flow, is the curl 0? And if it's not 0, which way is it pointing? And you go, how can I do that? Well, first notice, F is PI plus QJ plus RK. Now first notice, one thing they're telling me about this vector field. It's shown in the xy plane and looks the same in all other horizontal planes. So that's saying if I came up 1 inch, or 2 inches, or 3 inches, the fluid flow is going to be the same thing. It's all going this way. Well, look at all these vector valued functions. What's their z component? They're all pointing in this direction. What's their z component?
0.
Is any other component 0? Look at this vector right here. What's its x component? Remember, when you had a vector, if it looked like this is your x component, and this is your y component, right? How much do you go over x, and then how much do you go up y? What's my x component for these guys?
0.
Aha! So all of these arrows have p equal to 0, and they have r equal to 0. They just have something q. All right? Now, in addition, they said if you move up, you get the exact same arrows, right? Well, remember, if I wrote partial of q with respect to z, that is how is the y coordinate changing as I change the z coordinate. Well, if I change the z coordinate, I have this one little arrow right here. If I change z a little bit, is that arrow changing? It's not changing at all. So the partial of q with respect to z is going to be what? 0. Okay? And we also said p and r were 0. Well, geez, if p is 0, then the partial of p with respect to x, the partial of p with respect to y, the partial of p with respect to z, all of these are 0. And if r is 0, partial of r with respect to x, with respect to y, with respect to z is 0. So coming back here, let's see if we can eliminate a few things here. Since p is 0, and r is 0, well, in fact, it might be even easier to write it this way. We're going to go the curl of f is I, j, k. I think it'll be easier to do it this way instead of substituting into that horrendous formula. Let's just do it right here. Partial with respect to x, partial with respect to y, partial with respect to z of, you guys just told me p was 0, q does change, and r is 0. So look what I get here. I get I times the partial with respect of 0 with respect to y is 0, minus partial of q with respect to z, minus j times, eliminate row and column j's in, partial of 0 minus partial of 0, that's one big goose egg, plus k times partial of q with respect to x, minus partial of that with respect to 0 is 0. So that's my curl. Okay, now guys, del cross f equals this. Okay, so now I got my curl. Now remember, this vector valued function f is pi plus qj plus rk. Now, how is q, what's q? Q is your y component. Partial of q, in fact, let's write this out in your notes. Partial of q with respect to z is how is the y component of the vector changing as I change the z coordinate. Well, if I look at the vector I have here, and then I just change the z coordinate, so I just lift a little bit, since they told you the fluid flows the same as you go up and as you go down, what's the partial of z with respect to, partial of q with respect to z in this particular problem? Aha! Partial of q with respect to z is one big goose egg. So I go, oh, okay, I got that equal to 0. So I have 0i plus 0j plus the partial of q with respect to x times k. Now, what does partial of q with respect to x mean? Let's write it out. Partial of q with respect to x means, what is q? Which component? Y. It means how does the y component of the vector change? Y component, we should say, of the vector as we change the x coordinate. Okay, here's my vector. When I change the x coordinate, which way do I go? To the right or to the left? Let's go to the right because I don't have anything drawn for the left. If I go to the right, how's my vector changing? It's not changing at all. It's not changing at all. So does its y component change at all? Well, if the whole vector doesn't change, its x component, its y component, its z component don't change. So what's the partial of q with respect to x? 0. Excuse me, 0, just the number 0. So this turns out to be 0. So we have 0i plus 0j plus 0k. We have the 0 vector. We're trying to tie this together so things make sense to you. Remember, we said when you have a vector field where del cross f is 0, we say the field is irrotational. Well, shoot, people, if I've got my fluid flow going like this through the whole darn problem, am I curling at all? No, it's a straight flow. I'm just giving you, I want to get a sense of how this thing works. Okay, let's look at another one. This is number 10 they want us to look at now. And by the way, in your homework, you're doing the same ones. I think if I go through it and then, you can go try to do it yourself, and if not, go back and try to do it again. Now, before I start putting in, notice with this, we have f is equal to pi plus qj plus rk. All right, now notice, since we get the same picture at any level of z, that means the vector's not changing as I change z, which means if the vector's not changing, then that means the x coordinates, the x component's not changing, the y component's not changing, and the z component's not changing. So therefore we have the partial of p with respect to z, the partial of q with respect to z, and the partial of r with respect to z, all equal 0, because the vector's not changing. Okay? In addition, all of these vectors only have x and y components. They're not pointing up in the z direction. So in addition, r is 0. Okay? Yes?
How do you know if they are pointing up?
Because this is the xy plane.
So it'd be like 3D graph?
It would have to be a 3D graph, right. It would have to be coming like this a little bit. It'd have to have a z component lifting up into space, right? Okay. All right, now, let's write down let's do our curl. I think it's easier just to write the curl out for a second, because notice, life is very good here. To get your curl, del cross f, we have I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, p, q, and for r I'm putting 0 because none of these vectors have a z component. Doing the curl, I get I times, that's 0 minus partial of q with respect to z, minus j, that's 0 minus partial of p with respect to z, plus k times, if we do this one, this is partial of q with respect to x, minus partial of p with respect to y. All right, now a few minutes ago we said, remember, as I lift up here, and if I change the z coordinate, the vectors aren't changing. So we said the partial of p with respect to z, q with respect to z, and r with respect to z. The x component's not changing, the y component changing, and the z component's not changing if I change z a little bit or a lot. So all of these are 0, so this is 0, and we're stuck with that for a second. Now I have to think, what's going on here? Okay, we have to figure out what this is yet. All right, let's go back to the picture. We have partial of q with respect to x to figure out, and partial of p with respect to y to figure out. Okay, so I'm going to write down the two that I got to figure out. What the heck is the partial of q with respect to x? Now remember, f is pi plus qj plus rk. So q is the what? The y component. So I'm saying, how does the y component of the vector field change when I change x a little bit? Okay, well let's look. Here I am. What's the y component of that vector? As I change x a little bit, what's the y component of that vector? I'm thinking, In the first row, I'm getting 0. Let's do the next guy. Let's look at this vector and this vector. Is the y component changing? Ah! Look, he has the same y component's this much. If you're struggling a little bit, remember your components are, if I can't go from here to here, I go in the x direction this much, and then the y direction in that much. I go in the x direction this much, I go in the y direction this much. In the x direction, so this is my x component, this is my y component, this is my x component, this is my y component. Look at your y components. Are they changing? No. So what's the partial of q with respect to x? 0. So partial of q with respect to x is a big goose egg. All right, now let's look at the next one. The other one we had to do was partial of p with respect to y. What's p? X component. So I'm looking and I'm saying, okay, as I change the y component, is the x component changing? X component's this much, x component's this much, x component's this much, x component's this much. As I change in the y direction, is it changing? No. So this is 0. So lo and behold, I have 0I plus 0j plus 0k. We say this fluid field is irrotational. Okay, and as you look, it's not rotating, it's just sort of like flowing out is what it's doing. Okay, all right, let's do 11. All right, now looking at this, we could write this normally as f is equal to pi plus qj plus rk. But look at all those vectors. Their z component is 0. What else do you know? What else do you know? The y component is 0, isn't it? Sure, none of them have a y component. So this is some p plus the y component 0 and the z component is 0. So if I do curl del cross f, I have I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, of p 0, 0. So this is equal to I times, this is 0 minus 0, that's a big goose egg, minus j. This is 0 minus partial of p with respect to z, plus k times, this is k, 0 minus partial of p with respect to y. Now remember we said the fluid flow was the same if we increase z or decrease z, so the partial with respect to z was 0. So we have 0I plus 0j minus the partial of p with respect to y times k. I got to look at that yet. Okay, well let's look at it. We're trying to figure out, what do we know about the partial of p with respect to y? What are we doing? What is p? The what component? Okay, so we're looking at the x component, and which way are we moving? We're moving in the y direction. Okay, now look here. Right now the x component's negative. It's a little bit less negative. Then it's a little bit positive. Then it's even bigger in the positive direction. And then it's even more positive. What can you tell me about the partial of p with respect to y? Is it positive or negative? This is like a negative. Here you have like a -2. You increase it by 1. You get a -1. Or let's say it's like -3. Increase it by 2. It's a -1. Increase it by 2. It's a +1. Increase it by 2. It's 3. It's positive. Because as you move in the y direction, your x component's increasing. So if the partial of p with respect to y is positive, if this is positive, then what can you tell me about this vector? It's minus a positive, the k component's negative. The curl is pointing in the negative direction. Curl of f is pointing in the negative z direction. Okay, all right, we did enough of those. We got to define the next one that's a whole lot easier to do than the curl. All right, so far now, notice we had a scalar function f. Scalar. It was just like example f of x, y, z equals 2x plus 3y plus 7z. All right, the gradient of f gave you a vector function. Then we have f being a vector function, and we learned how to do the curl f today, which is del cross f, and that gives us a vector. Now we're going to have a vector function f. We're going to do something called the divergence, which we're going to write as del dot f. Okay, remember how to do dot product? Well, look here. The del with an arrow on it is going to be thought of as the partial with respect to xi plus the partial with respect to yj plus the partial with respect to zk. And if we dot it with f, which we've been writing as pi plus qj plus rk, when you do dot products, you normally multiply this plus multiply this plus multiply that. So you'll get the partial with respect to x of p plus the partial with respect to y of q plus the partial with respect to z of r. And that's what the divergence is. The divergence of f is partial of p with respect to x plus partial of q with respect to y plus partial of r with respect to z. It's that easy. So what we want to do is we just want to evaluate the following divergence, which is real easy. For this one, del dot f is just, you take your x component, you take the partial of that with respect to x, you take your y component, take the partial of that with respect to y, plus take your z component, take the partial of that with respect to z. That's all you're doing. So let's see. That's going to equal, what's the partial of that with respect to x? 2x yz. What's the partial of that with respect to y? 2x yz. What's the partial of that with respect to z? Oh, 2x yz. So we're going to have 6x yz. It's that easy. Not hard. Okay? Let's do another one. Next one we want to do is we want to figure out the divergence of g. You can write it as del dot g, or you can write it as div of g. Either way, you take your x component and you take the partial of that with respect to x. You take your y component and to take the partial of that with respect to y. And you take your z component and you take that partial with respect to z. We just have to remember, how do you differentiate logarithms? If you're differentiating log u, it's 1 over u times the derivative of u with respect to x. So what's the derivative of xz with respect to x? Z. Derivative of log u is 1 over u times, we got to differentiate yz with respect to y, that's z. Derivative of log xyz is going to be 1 over xyz times, what's the derivative of xyz with respect to z? xy. And lo and behold, let's see, we have a pair of z's cancel, pair of z's that cancel, pair of x's cancel. So we have 1 over x plus 1 over y plus, oh, y's canceled also, 1 over z. And we're finished. So the divergence is a piece of cake compared to the curl. Didn't have to work too hard at all. Okay, exact same problems, but this time it's going to be a little bit less painful because, I mean, with the curl, you've got 6 partials to deal with. Divergence, you just have 3 to deal with. So they want us, we're supposed to look at the same vector fields in the xy plane. Since it looks the same in all other horizontal planes, all partials with respect to z are 0. So the partial of p, partial of q, partial of r will all be 0. So we look at this function, okay, and I say, okay, if f is equal to pi plus qj plus rk, all of those vectors are pointing in what direction? What direction are they pointing? The y. So if they're all pointing in the y direction, what's their x component? What's their z component? So this is 0, and this is 0. So this vector function is just f equals 0i plus qj plus 0k. So the divergence of this function is the partial of 0 with respect to x plus the partial of q with respect to x, with respect to y, plus the partial of 0 with respect to z. So my divergence is just partial of q with respect to y. Okay? We doing okay? All right, now q is what component? Y. So we're looking at q is the y component. And we're going to be looking at the y component, and we're going to move in what direction? Okay, so let's take this vector right here. If I'm right here, and I move in the y direction, positive y direction, how's my y component changing? Decreasing. So what can you tell me about the partial of q with respect to y? It's going to be negative. Okay? Interpreting what's happening to the vector field. You all with me? Q was the y component. It's the y component. If we're looking at the partial of q with respect to y, we're saying we're looking at the y component, and as we move in the y direction, how is the y component changing? As I move in the positive y direction, the y component is getting shorter. It's decreasing. Okay, let's do another one. This one. Again, we could write our vector valued function f as pi plus qj plus, what's its z component? 0. Okay, so the divergence of f is the partial of p with respect to x plus the partial of q with respect to y. Now let's look at these. If I'm doing partial of p with respect to x, p is what component? X. Which direction are we moving? Positive x. Okay, so let's just look at a few of our vectors. As I move in the x direction, what's happening to my x component? Bigger. Okay, let's try this one here. This is my x component, this is my x component, this is my x component, this is my x component. Heavens! Even that one, they're getting bigger. So if the x component is increasing, partial of p with respect to x is going to be positive. We also had to figure out partial of q with respect to y, right? So if I'm doing partial of q with respect to y, we're looking at the y component. And which way are we moving? Y direction. Okay, so I'm saying, okay, here my y component is 0. Here's my y component. Here's my y component. That's my x. Remember to draw your components. Like if I can't walk from here to here, I'll walk this much in the x and then that much in the y. So look at your y component. It's 0, this much. Aha! It's increasing. So it's positive. So my divergence is going to be a positive plus a positive, which is a positive. So I can tell by looking at the vector field what the divergence is going to do. Okay, let's do one more. Again, this is vector function f equals pi plus qj plus rk. But it has no z component. It also has no y component. Do we all see that? Because they're all pointing in the x direction. So this is 0 and this is 0. So my divergence is the partial of p with respect to x plus the partial of 0 with respect to y plus the partial of 0 with respect to z. It's just the partial of p with respect to x. So if I look and I say, what do I know about the partial of p with respect to x? P is the x component, and we're moving in the x direction. So we're going from a negative to a, oh, look at those. How is my x component changing as I move in the positive x direction? They're the same. So what does the partial of p with respect to x equal? 0. It's 0. Okay? All right. Now, the following, I'm going to do a few of these. In fact, I'm doing 6 of them. I'm assigning number 12 in your homework. I do have the answers posted under the assignments on Blackboard. So you can go, after you do them, you can check to see if you got them right. All we have to do in these is it says f is a scalar field, and f with a bar over it is a vector field. We're supposed to look at what they're writing, and we have to decide, does it make sense? If it doesn't make sense, you just say it's meaningless. If it's meaningful, I want to know, after you do whatever they tell you to do, are you getting a vector field or a scalar field? Okay, now notice, you take a scalar function and you apply the gradient to it, and you get a vector field. If you have a vector f, and if you take the curl of f, you get a vector, right? The curl of f gave us another vector field. Notice the divergence, that gave you partial with respect to x plus partial with respect to y plus partial with respect to z. It just gave you a scalar. So the divergence is dot product. It gives you a scalar, just like it did back in chapter 13. And cross product yielded a vector. Curl and divergence only can be applied to vector valued functions. You don't say what's the curl of 2x. It doesn't make sense. You follow? It has to have an I, j, and k component. So for this one, you say, oh, she's taking the curl of a scalar. That doesn't make sense. We take the curl of a vector. So this is meaningless. This one is gradient of f. And maybe you might remember the gradient of f was partial of f with respect to xi plus partial of f with respect to yj plus partial of f with respect to zk, which is a vector field. So that's a vector, so it does make sense. Can I take the divergence of a vector valued function? Yes. When you take the divergence of a vector valued function, what do you get? Scalar. Because why? Because this is equal to partial of the x component with respect to x plus the partial of the y component with respect to y plus the partial of the z component with respect to z. You add them up, you're just getting one term. You're not getting anything with i's and j's. Now, when you take a scalar function and you take the gradient of it, what do you get? A vector. And you can take the curl of a vector. When you take the curl of a vector, you get a vector. Okay, can I take the gradient of a vector valued function? No, meaningless. When I take a vector function and I take the divergence of it, what do I get? Scalar. And can I take the gradient of a scalar? Yes, and when I take the gradient of a scalar, I produce a vector. Okay, there's multiple ones after that, but you can go through and do it just thinking through. Okay, we have a nice little theorem here. I'm going to prove, I have it actually, the proof printed out so you don't have to copy it. The divergence of the curl of f is equal to 0. Notice, if you take a vector function, you take the curl of it, you're producing another vector function, and we're saying if you take the divergence of that vector function, you will get 0. Now you might wonder, why does anybody care? You'll see there's an exercise where this is going to be helpful. The proof of this is this. The divergence of the curl of f is del dotted with del cross f. So del cross f has this for its x component, this for its y component, this for its z component. And then I'm taking the partial with respect to x for this piece, partial with respect to y, partial with respect to z. If I take the partial with respect to x of these guys, I get this. Partial with respect to y of these guys, I get this. Partial with respect to z of these guys, I get this. But Leclerc's theorem says, oh, if I take the partial of r with respect to x with respect to y, or with respect to y with respect to x, they cancel. Partial of q with respect to x with respect to z, with respect to z with respect to x, they cancel. And these guys, the order's just indifferent, but one's a plus, one's a minus. Everything cancels, and we get 0. So what we have proven, if you give me any vector-valued function, if I take the divergence of the curl of that function, I will always get 0. Okay, now why? Who cares? Is there a vector field G such that the curl of G is equal to this? So I've got this function, and I'm wondering, can I find some G that if I take the curl of this, I will get this? Okay, well, if I can find some G so that the curl of this is equal to this, notice the divergence of the curl of G is equal to the divergence of yzi plus xyzj plus xy times k, which equals partial with respect to x of yz plus partial with respect to y of xyz plus partial with respect to z of xy. Partial with respect to x of this is 0. Partial of this with respect to y is xz. Partial of this with respect to z is 0. We get xz. Well, we just proved a few minutes ago that if you give me any vector-valued function, if I take the curl and then the divergence, I get 0. So if I could find some g so that the curl of g was equal to this, if I take the divergence of the curl of g, that always has to equal 0. But the divergence of this gave me this, which is not 0, so no. It can't happen. You can't find some g whose curl is equal to that. So all you have to do is take the divergence of this and show that you're not getting 0. So it's not worth your while to find what the curl of worth your while to find some g whose curl is equal to that. Okay. Show that any vector, now we have a couple little, your book likes you to do a few little proofs, and I want to show you these proofs are very, very easy. Show that any vector field of this form, where f, g, and h are differentiable functions, is irrotational. What does irrotational mean? It means its curl is equal to 0. Okay, now what does this mean, f of x? That means f is solely a function of x. Do any y's show up? Do any z's show up? So if f is totally a function of x, what's the partial of f with respect to y?
0.
What's the partial of f with respect to z? G is totally a function of y. So what's the partial of g with respect to x?
0.
With respect to z. So if I go to do my del cross f here, I go, oh, I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, f, g, and y. This equals I times, oh, why did I put y there? H. I'm going to go partial of h with respect to y minus partial of g with respect to z minus j. Eliminate that row and column. Partial with respect to h of x minus partial of f with respect to z plus k times partial of g with respect to x minus partial of f with respect to y. But h is a function of z, so the partial of h with respect to y is 0. G is a function of y, so partial of g with respect is 0. So that gives me 0i. H is just a function of z, so this is 0. F is a function of x. This is 0. G is a function of y, so partial with respect to x is 0. And f is a function of x. This is 0. And so therefore we get the 0 function. So therefore, since the curl is the 0 vector, the function f, the vector field f, is called irrotational. Okay. If the divergence of a vector field is 0, we use the adjective that the function is incompressible. So if I want to show that this function is incompressible, I take the divergence. So you have the partial of f of yz with respect to x, plus the partial of g, which is a function of xz, with respect to y, plus the partial of h of xy with respect to z. But f is just a function of y and z, so there's no x, so you get a 0. G is a function of just x and z, there's no y, you get a 0. H is a function of just x and y, there's no z, you get a 0. So the divergence is 0, and that's what incompressible means. Pretty easy. Okay, now before we call it quits, I just want to take 1 second and show you that with what we did today, we can rewrite Green's theorem using the notation that using the curl that we did today. What we did last time in section 17.4, if you had a lovely little curve, if you're integrating around the curve in positive orientation, remember positive orientation is thinking a little guy walking along the edge and his left arm is always pointing inside. So you have to go this way. And we didn't prove it last time, but I told you they had a little mini proof in your textbook. The partial of p dx plus q dy was equal to this. Okay? Now notice, vector f here in Green's theorem that we did the other day was pi plus qj plus, I could write that as 0k. So if I wanted to go del cross f, I would go I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, p, q, and 0. Now notice this is equal to I times partial of 0 is 0 minus partial of q with respect to z. Okay, minus the partial of q with respect to z. Well, q is not defined with respect to z, so this is 0. Okay, minus j. When we go minus j, you have partial of q with respect to x minus partial of p with respect to y plus k. Yes. K, P, Q, 0. Oh. Now what's the problem?
Partial of 0 with respect to x if we're doing the j column.
Partial of 0, the j column. Okay. Minus j times, oh, yes, thank you. I go, partial of that is 0 minus partial of p with respect to z. Okay. Plus k times partial of q with respect to x minus partial p with respect to y. Now, I crossed this out as 0. Let me talk for a second. Remember, when you did your homework last night, p was a function of x and y, and q was a function of x and y. There were no z's in your homework last night when you're going along that curve because you're in two-dimensional space. So if p is totally in terms of x and y, and q is totally in terms of x and y, the partial of q with respect to z is going to be 0. The partial of p with respect to z is going to be 0. And you're going to be left with just this y component. Okay? So coming back here, we just figured out that the curl of f dotted with k dA is equal to, the curl was partial of q with respect to x minus partial of p with respect to y times k. And we're dotting it with k dA. Well, when you did dot product, what do? You multiply your x components plus multiply your y components plus multiply your z components. Well, I don't have any x and y's, but I do have k's. When I multiply that together, I get that, which is what I had inside. So the point is, I don't know why you would want to at this point, but you could rewrite Green's theorem using this notation that we learned this time. we'll find in a few sections further that there's a reason why we want to do that. In this section, it doesn't even show up in your homework, but I just wanted to mention it. So, for this particular time, I want you to read pages 1126 to 1131, and then on page 1132, you want to do 1 through 11, the odds, 12, 13 through 21, the odds. All right, and by the way, 12, I have the answers posted on Blackboard under your assignment. Okay, I'll see you next time. Bye-bye.